So based on the problem here, that they give you some information about what to do in terms of the notes. So make sure, again, you watch that video. What you're trying to prove here is the side angle side really work. And in terms of the tools, if you want to move a triangle, you click on the center and you can move it. So you just hold the button down and let your mouse button down. You just do like a click and release the mouse button. It should give you the tools. You have a reflection tool, a rotation tool, and this one's the dilation tool. And if you click on the question mark up here, based on the video that I put together, it will give you all the information you need about the tools. So in doing this problem, if I want to put these two triangles on top of each other using Euclid's idea of superimposing, which transformations would I use? Which transformations will I use? Because based on Euclid's proof of congruent triangles, he wanted to superimpose one triangle on top of the other to prove that triangles really do match up. And that's what they're asking you to do in this lesson. So what rigid transformations are we using here? The rigid transformations are translation, rotation, reflection of the three rigids. Translation. So we can do a slide. So I can get for example, I can get point B and point E lined up, for example. That would definitely be a good first start. The translation definitely going to get used. And rotation would be a good choice. So I can put rotation here, and I can try to get the triangles to match up. Now, the one thing I found about this particular activity is that if you did the rotation first, and then did the translation second, you're going to have a much better chance of getting the triangles to match up. So it's not necessarily that the order is bad when you say translation first, rotation second. It's just that I found with this activity, if you do the rotation first, then translate second, you get those triangles to match up a lot easier. Anybody who didn't get the triangles to match up? Anybody have any questions? So this is called superimposing. This is what Euclid called it. And so because the triangles are superimposed, all the measurements match up, the triangles are considered to be congruent. So the second part of the problem says, Emma asks, what about these triangles? How can we make them coincide? Discuss any previous strategy, explaining why this proves that the pair of triangles will be congruent using side angle side. So most of you are close to somebody in class. If you can have a real quick discussion about how you would prove that these two triangles really are congruent, what would be those rigid transformations that you would be using, and then we'll have a discussion in about 90 seconds. So William, what transformations would you use here to prove these triangles are? We're still at 20, part B. This is what you're supposed to discuss with, I guess, be Henry, supposed to. Do you have an answer? Okay. Eddie? You use all three of them? You use, so which one would you do first? Okay, so you want to basically flip the triangle over to reflection so that 4.5 will actually line up correctly with the 4.5, and then you translate it and then rotate it. When you translated it, did you line the two triangles up? Would you line the triangles up in any way special to make sure that the rotation worked?
I lined it up with
the one that's marked, or does it really matter? The one's marked. Okay, so you line up with the angle that's marked, and you do the translation, and then do the rotation at that point. Anybody else do it differently? Different order? Reflection, then translation, line up the vertices of the marked angle, rotate the triangle. Anybody else do it differently? So problem 621, they're still asking you to use those tools. And so which transformations did you use to be able to line the two triangles up? The transformations. That would you use?
two reflections and transformation.
What transformation? You mean translation?
Oh, yeah.
So you did, what was the first two things?
To reflect.
Two reflections and then a translation?
Yeah.
Okay. Anybody else do the different set of steps? So two reflections and then translation. Did you, and what, you said reflection?
Yeah.
So I'm going to assume you're trying to get the triangles to have the same orientation like this. In the end for the translation, everything matches up this way. So on your first reflection, where did you place the line at? Did you make it like real close to this, or? Okay. Is it possible to do it in one reflection? Or do I have to do a second reflection? Two. So I can do it like this, for example, and then I can do a second, maybe. There we go. Second reflection going the other direction. Like, so something over here, for example, to get the angles to line up like this. And then you do the translation to kind of get things line up. That's pretty close. So you do that second reflection to get the angles to match up perfectly. Anybody else do it differently?
I did a rotation and then I did a
You did this a rotation.
I'm pretty sure I just rotated it.
This angle right here, it was over here on this side, so there's no way of getting this blue angle to line up with this angle without doing at least one rotation, I believe. So I can take this shape here and I can rotate it, for example. But you did rotation like this. So you did a rotation first and then translation second like this. Okay, all right. Anybody else do it differently? How many of you did the rotation then the translation? 30 of you? Okay. All right. So the questions they're asking in the lesson. Janet is talking about the this time we had to do something a little bit differently, and so even though these points are on top of each other, such as C and F, he thinks that there's for a bit it adds up. I think that the angles B and E are congruent. How does she make sure that that's true? How does she know that that's true? That angle E and angle B, they're called double prime, which means it has to be moved. How do we know that they actually are congruent? All right, so going back to the sketch itself, the angle of B and the angle of E, they're marked to be the same measurement. They both have a single tick mark. So if I rotate this thing and stick it one on top of the other, they better match up because they're marked to begin with have the same angle measurement. So the rotation, it gives me the double prime because we're doing some kind of movement to it. So that they move the top triangle versus the bottom. Patrick talks about this idea of identical between B double prime, C double prime, and E, F, and A double prime, C double prime, and D, F. Is Patrick correct that those segments have to be the same length? Is he correct? Question B. So in this problem, they're saying that A, B, and D, E are the same length. They're saying that right up front in terms of this problem. And they're also saying that angles AB and BE are the same measurement. So we are looking at side angle side. And so we have a pair of sides here. We have an angle here and an angle here. So this is angle side angle. And we're trying to prove that side angle side really does work here. And so Patrick is talking about the fact that BC and EF have to be the same, and AC and DF have to be the same. and that is the other two pairs of sides. And why do those other two pairs of sides have to be the same?
Because you already have all the angles and you have a scale factor of 1.
Because we have a scale factor 1 between the two sides I've marked up there, AB and DC. So that makes the triangles the same size. That means the other two pairs of sides have to match up. Because we already have the triangles being similar. And we also have the fact that they're congruent because of that pair of sides being the same. So that means the other two pairs have to be the same. And that's why Patrick's comment here is a true statement. The third one is they must be congruent because this means point C is the same as point F. Why do those two angles have to be the same? Why do the two remaining angles that are not marked, which are C and F, why do those two angles have to be the same?
So you already have two angles, and you can only have a very specific, like it has to add up to 180, so you have to subtract 180.
So if you have two pairs of angles that are the same in both triangles, you have two pairs of corresponding angles, if I subtract both those numbers from 180, what's left over has to be the same number, which means the last two angles have to be the same answer. And then the last question, Eddie says if we need a reflection to have this triangle on top of each other, does that affect the result? And actually we did what? 2 reflections, right? For yours, like that? Yeah, so the answer is, does doing reflection going to affect the result? The answer is no, but we've got to make sure we do 2 reflections. And we did this actually back in chapter 1, that when you do double reflection, that's the same thing as a rotation. So a double reflection done right should be the same as a single transformation that's a rotation. So the last problem is for 22, and you're being asked to go through and decide whether these triangles are congruent or not based on the information. So go ahead, and if you've not finished those, go ahead and look at those last 3 problems, and we'll talk about those here in a couple of minutes. All right, so I have 2 triangles here that are congruent by side. It actually giving you a hint here. How can you use this information to be able to prove that angles A and D have to be the same? Your hint is, can we use law of cosine? Could I use law of cosine to prove that the angles A and D, or it could be any other pair of angles with law of cosine? Let me do that. I'll pose the question differently. I'm thinking of 3 side lengths, 12, 15, and 20. And I ask all of you to do 12, 15, and 20 and to find the angle between the 12 and the 15. So if you drew that triangle, we use those 3 numbers, would all of us get the same angle using the law of cosine? True? If I would just select any 3 lengths, as long as it makes a triangle, and I ask you to find a specific angle on that triangle based on the 3 numbers I give you, should we get the same answer for the angle? Does it matter what numbers I choose as long as the 3 numbers make a triangle? Will it ever make a difference for side, side, side? The answer is it won't make a difference. I can choose 3 numbers as long as it makes a triangle, because we're going to do a squared plus b squared minus 2ab cosine of that angle equals c squared. If I stick in the a, the b, and the c, the sides, and we're using the same 3 numbers, that angle better be the same answer when we're finished. Kind of like Pythagorean theorem. If I have 2 sides, and the other triangle has the same 2 sides, won't the third side be the same answer? If let's say I'm looking for a missing leg or a missing hypotenuse, should I not get the same answer? The answer is sure, as long as the numbers are set up the same way. If I give you 2 legs or a leg and a hypotenuse and they're the same numbers on both triangles, I should get the same answer for the third side. So that's why they give you a hint here using the law of cosine. And how about the other one? If I have angle side angle congruency, how can I use that to prove angle side angle?
The exact same thing, because you have 2 angles on one side. The only change is just a little bit different.
Okay. Anybody else? So can we agree that if I have 2 angles in both triangles, the third angle will be the same? If I place it in the third angle, do I not now have an angle side angle pattern? if I choose the right two angles